We are going to try and understand all about hexadecimal number system. So we'll look into what is hexadecimal number system, how does it work, and we are trying to learn about the number system conversions from binary to hexadecimal and hexadecimal to binary. Most importantly, do subscribe. I repeat, do subscribe to get more information on the updated videos on YouTube. Thank you. Let's continue. The hexadecimal number system, as it says, it has got 16 digits together. That simply means the base is 16. Now we need to find out what are the 16 digits with us. So if we look at the numbers we have got the numbers 0 to 9, and then to make it 16, we will have to use the numbers 10 to 15. This together will give us a set of 16 digits as required by the hexadecimal. But the question arises here, how would you write the numbers 10 to 15 in binary? Because if you look at it closely, 10 is 1 and 0, which are two different bytes. So let's try and put them together. So to put this together, you have got the numbers 0 to 9 remaining as it is. Then let me write 10, 11, 12, 13, 14 and 15. These are represented by uppercase or capital A, B, C, D, E and F. So putting it together, the hexadecimal number system is comprising of 0 to 9 and the alphabets A to F. The hexadecimal number system is very closely related to the binary number system. Which relates to the equation 2 raised to the power 4 is equal to 16. That simply means every hexadecimal digit is made of 4 bits. To understand this whole scenario, we are going to convert the hexadecimal into the decimal, which is 10, 11, 12, 13, 14 and 15, and back to the binary. Let's do the tabular form. To understand the relation between denary, hexadecimal and binary, I'm going to use the table here. So this is going to be the denary. This column I'm going to use for hexadecimal, and this column for the equivalent binary. So let's get started. For hexadecimal, we need the 16 digits. So let's write the 16 digits in terms of denary. It's 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Until 9, there's no issue. We need to continue writing in denary the digits further: 10, 11, 12, 13, 14 and 15. Let me make this a little bit longer to complete the table. So now let's see what is the equivalent hexadecimal. For the digits 0 to 9, they remain as it is. So it will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now as we just learned a while ago, the 10 is represented by the capital A or the uppercase. So let's put it together: A, B, C, D, E and F. What does this mean? This simply means that whenever you want to write a denary number 10 in hexadecimal, you will have to use the uppercase A. Remember, you cannot use the lowercase because it has got a different value altogether when it's stored in the computer. Now let's look at the binary. We just learned that the binary and hexadecimal has a relation of 2 to the power 4. So let's use that. 2 to the power 4 gives us 16. That means each hexadecimal digit has got 4 bits together. So we have to remember this. So if you talk about 0, it's going to be 4 zeros. 1 is 3 zeros and 1. 2 is simply 10. So we need to take the 2 in denary and convert it into binary. I do hope you remember the division method. So let me quickly recall it with you. So 2 you need to divide the number by 2 continuously. To 2 ones are 2, the remainder is 0. 2 times 0 gives you this, and then the remainder is 1 in this case. So basically you have got 10, and to make the 4 bits you need to put the zeros onto the left side. Remember, the numbers are added always onto the left side. So this is represented by 0 0 1 0. The 3 is represented by 0 0 1 1. The 4 is represented by 0 1 0 0. 5 is represented by 0 1 0 1. Wherever you forget, we can always do the quick calculation so that you are not confused, and we can do that. So let's keep doing that, and it will give you some good practice also. So let's take number 6 now. So 6 is 2, 3 times 6, the remainder is 0. 2 1 time is 2, remainder is 1. 2 0 times, and the remainder is 1. So it becomes 1 1 0. So it's represented by 0 1 1 0. Let's quickly do the 7 now. I'm going to use the same space. So 7 is over here. 2 3 times, and remainder is 1. 2 1 time, remainder is 1. 2 0 times, and the remainder is 1. So it's 111 for you. If you're comfortable using the subtraction method also, you might want to give it a try. I'm skipping the 8, which is 1000 for now, and the 9, which is represented by 1001. Now to convert the 10, let's use this again. Let's use the space, and then 10 is represented by A, but logically you cannot convert A into a bit. So whenever you have to write the digit in hexadecimal A, you have to use the equivalent denary 10 and then convert it into binary. So let's do that here. 2 5 times, remainder is 0. 2 2 times, the remainder is 1. 2 1 time, the remainder is 0. And 2 0 time, and the remainder is 1. So basically 10 is represented by 10 10. How does this work? So if you have got a hexadecimal, let me use it in red, A, it will be represented by the denary 10 or represented by the binary, which is 10 10. That's how it relates together. So similarly, let's do for B, which is in denary the number 11 and is represented by 10 11. C, it's represented by 11 0 0. It's easy to put the numbers 1 1 0 zeros together, but it's not called as 11, it's 1 1 0 0 in real. To avoid making mistakes, you could just call it that way. So it's basically read as 1 1 0 1, and then E is represented by 1 1 1 and 0, and F is represented by 4 times 1. So this completes the relationship between the decimal, hexadecimal and binary. With time you get used to it. Once you remember the denary to hexadecimal equivalent, you can always convert it into the binary. You do not have to try and memorize the entire table. As you can see, it's very easy to convert it. Apply this knowledge you have gained together to see a real conversion. So we are going to convert the binary to hexadecimal, and I have taken an example over here, and this is, let's say, in binary. Since we do not know what is the equivalent hexadecimal, I'm going to put a question mark and then the base 16. It's very important to use the base because it clearly identifies the value whichever you are using to the number system, or it relates the value to the number system. So this is binary because logically this could also be a denary number. So now let's get started. Use the relationship 2 to the power 4 is equal to 16. What does that mean? That simply means starting from right hand side. And why is this? Because numbers always work from right to left. Right hand side, group the digits in 4. And then the question arises, if you are falling short of digits, if there are less than 4 digits in the last group, add zeros. That's your second rule. What is the next rule? Replace each group with equivalent denary number. And the last rule is replace each denary number by the equivalent hexadecimal number. Okay, let's see how these are going to work. So going back and taking the numbers, let me just make the groups first. So this is going to give us one group, then second group and third. Fortunately, we do not have to add extra zeros because we have got the 3 groups. So I'm just going to write the groups over here first. The first group is 1, 3 zeros. The second group is 0 and 3 times 1. And the last group is 1, 1, 0, 1. Now these are the 3 groups and this is the binary. So this is the first step, 2 to the power 4, making the groups in 4. Now we need to put the decimal equivalent. I'm just going to quickly show you how you could use the decimal equivalent. If you remember, it's great. If not, this is how we are going to put it. Let's take the group 1. This is my rough area. And 0001. Remember, 2 to the power 0, these are going to be 0, so it's going to be 0 again. 2 to the power 0 is 1, so it's going to be 1. So this becomes 1. I'm going to erase this, take the next number, which is 1110. So it's like 1110. So this becomes 2 to the power 0, which is 1, 2 to the power 1, 2, 2 to the power 2, 4, and 8. So this is 8 plus 4 plus 2 because this is 0. So it remains 0. 8 and 2 is 10. So this becomes 14. So for now, we are just going to write 14. And then we are going to use the next, which is 1011. So let me use that. 1011. This is 2 to the power 0, which is 1, 2, 4, and 8. This is going to be 0. So this gives us 8 plus 2 plus 1, which is 11. So now we have got the decimal equivalent. Let's put the hexadecimal. So that's our last step over here. Hexadecimal. 1 is represented by 1. If you remember, we'll just quickly erase this so that we can put the digits together. So we had starting from 10, 11, 12, 13, 14 and 15. This was capital A, or rather this is capital A, B, C, D, E and F. So let's use this. So 14 is represented by E and 11 is represented by B. So erasing this rough area, we actually get the final answer that 1011 1110 0001 in binary is equivalent to BE1 in hexadecimal. Do remember to write the base. I hope this is clear. Let's take one more example over here. So this is the number I have taken and it's in binary, and the question is how do we convert this into the base 16? Sorry, it's the other way around. It should be what is the equivalent in hexadecimal. So base 16. So be very careful when you write the digits. Let's make the groups of 4 digits. So this is going to be giving us the first group. So 1, 1, 1 and 1, the first group. The next group is here. So it's 1, 1, 1 and 0. And then we have got the next group, which is here 0, 1, 0, 0. So these are the groups. So let's put them together into the binary. You could do it straight also. I'll do it here and then I'll erase it. So 2 to the power 1. So let's start. 1, 2, 4 and 8. 8 and 4 is 12, 13, 14, and this is going to give us 15. So 15. This is converting it into the decimal or denary. So let's get back to the next number. This is 1, 2, 4. We do not need the 0 because it's going to give us 0 anyways. 4 and 2, 6 and 1, 7. Let's try this. We don't need this 1, so it's 2. So this is going to give us just 2. Now we need to convert this. This is what we have got in the decimal. We need to convert this into the hexadecimal. So hexadecimal, 2 remains 2, 7 remains 7, and if you remember 15 is the last character or the last digit, which is F. So this is going to be 27F in the hexadecimal. I hope it's clear now. Generally speaking, it remains very straightforward, and let's quickly have a look at an example. So I'm putting it as example 1, and the hexadecimal number I'm using is, let's say, 45A. So this is an hexadecimal, so base 16, and we need to find out what is the binary equivalent, so base 2. Now to do this, there's a few steps and we are going to deal with that. The very first thing is you could directly use the hexadecimal equivalent values of these digits and put them together. So I'm just going to write it over here. Directly use the hexadecimal to binary values and put them together. Of course, it sounds very easy and straightforward, but the only catch here is you would have to get the table in front of you. So that's the deal. The second way is convert. I'll put the or here so that it's not confusing. Or convert the hexadecimal digits into denary and convert these further into binary. These are the two ways of doing it. Both are pretty much straightforward. Let's try them. And one thing which I'm going to put it as note here is, irrespective of which way you use, every single hexadecimal digit must be written as, or must be written in 4 bits of binary. So now we are going to try this example we have just taken over here. So continuing with the example, which is 4, 5, A, given in hexadecimal, we'll try and figure out the binary. So I'll use the second method because I do not want you to stress memorizing the hexadecimal conversion table, because it could just be a little tricky messing up with zeros and ones. So let's do it individually. So I'm going to write these 4, 5A here. The first step is convert the hexadecimals into denary. So let's do the first step, denary equivalent. So what is denary for 4? It's 4. 5 is 5. A is 10. This is very important. Now the next step is convert these into binary. Okay, let's take the first digit as binary. I'm going to use this area on the left to do the rough work. So first we are taking is 4. So to convert this denary into binary, I'm using the division method. So 2 times 2 gives us 4, giving remainder 0. 2 times 1 gives us 2, remainder is 0. 2 times 0 is 0, so giving us the remainder 100. So if you look at it, the 4 is got 100 and it's 3 bits. to the left, you're going to add 1 0 to ensure it's 4 bits. Now let's do the next digit, which is 5. Let me erase this, and we're going to use the digit as 5. Quickly, it's a bit of lengthy process, but it ensures your conversion has got the perfect result. So 2 times 2 gives you 4, the remainder is 1. 2 times 1 gives you 2, the remainder is 0. 2 times 0 is 0, and the remainder is 1. So this is 1 0 1. This is very tricky. We need to add the 4th bit as the 0 over here before we can combine. Look at this. Every single denary digit has to have the 4 bits. That's where we need to be a little bit careful. Though at times we are getting 3, put the 0 onto the left side. So let's try and get the equivalent for 10. So 10, 2 5 times gives you 10 with a remainder of 0. 2 times gives you 4 with a remainder of 1. 2 1 time gives you 2 with a remainder of 0. 2 times 0 gives you 0 with a remainder of 1. So for 10, we have got 10, 10 or 1 0 1 0. Now we are going to put this together to get the binary number, which will become 0 1 0 0. You need to combine these in the same order as you have got it. 0 1 0 1 1 0 1 0, which is the binary equivalent. Let's practice this taking one more example. So example 2, and remember we are converting the hexadecimal into binary. So the example 2, we are taking a bigger digit. So let's take B, F, 0 and 8, which is in hexadecimal. We need to find out the binary equivalent. Bit lengthy, but perfect way of doing it. Convert it into denary. So I'm going to write it here: B, F, 0 and 8. The first method, the denary equivalence. So denary is for B. Remember, if not, here it's again for you. It's A, B, C, D, E, F. It's worth writing rather than making a mistake. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So let's use this. B gives us 11, F gives us 15, 0 remains 0, and 8 remains 8. Now let's put this into binary. I do hope you're expert in converting these now. So I'm going to use them directly. So this 11 gives us 1 0 1 1. F, which is equivalent to 15, gives us 1 1 1 1. 0 of course remains the 4 times 0, and 8 gives us 1 and 3 zeros. To put it together, we get 1 0 1 1 1 1 1 1, 4 times 0 and 1 with 3 more zeros. Don't forget to put the base as binary. I hope it makes things clear.